Here we are done with Kepler's first law, and now we'll start with the Kepler's second law, which is law of area, right? We have already discussed. So according to second law, let us see the statement. The radius vector drawn from the sun to the planet sweeps out equal areas in equal interval of time. Okay, so according to the statement, if we draw the radius vector from the sun to the position of planet, so here we have four position in a diagram. So let us say this is position A, this is position B, and planet is moving from A to B here. Then planet goes here and then it moves from C to D. So these are the two different positions, C and D. So if I consider here that area is A1, okay, and here I consider area as A2, okay, and here I consider the time taken by planet to move from A to B is T1, and time taken by planet to move from C to D is T2, okay. And if that time taken is same, like T1 is equal to T2, so these two intervals are same, then according to the Kepler's second law, that area A1 must be equal to area A2. Again, see the statement. The radius vector drawn from the sun to the planet. Here we are, if this is the point S and this is point A, SA and SB will be the radius vector. Correct. So we have drawn this radius vector. Sweeps out equal areas in equal interval of time. That means if this radius vector is moving from A to B, okay, and area covered is A1. This radius vector SC moving from C to D, then that area covered is A2, and if this time T1 and T2 are same, then we get area A1 equal to A2 according to the second law. So here can we prove that? So the answer is yes. So here let us suppose we are considering this is the position of sun and this is the position of planet, and here we are taking this small displacement, very small displacement we have taken, okay. Let us call this displacement as d theta and this distance as r. So definitely this distance will be r d theta, okay. If I want to calculate the area in that case, so I will say the small area dA covered here will be half into base into height, correct. And I would like to know about the change in area in that case, so I will just differentiate both the side with respect to t. So dA by dt is equal to half into r into d theta by dt. Now I know that this d theta by dt is omega, which is the angular velocity, and if we do this r omega, it will give me the linear velocity. So I will call it as half into r into v, okay. Let us consider this as equation 1. Fine. Then I also know that the angular momentum also I can calculate in that case. So angular momentum in a vector form is m into r cross v, correct. So if I take its magnitude, I'll get this as m into r into v, and let us call it as equation 1. And if you compare your equation 1 with equation 2, you will get your change in area, which is dA by dt as L by 2m, right. Now here we can say angular momentum is constant as net external torque is 0 and mass of the planet is also constant, right. So the ratio L by 2m is constant. That means here we are getting dA by dt as the constant value. That means that the area covered in the specific interval of time is constant, correct. So that means it is indirectly proving our Kepler's second law, that the radius vector from the sun to the planet sweeps out equal areas in equal interval of time. Hence it is proved.